All right, this is Auto chapter 10, section 2 and 3. All right, finding arc measures. Uh, so if we have a circle, all right, we have a radius, or actually the center of the circle. Call that center C. We have some point up here on the circle itself, and a point here on the circle here. And we have some other point here. This angle ACB that's called a central angle. And it's called a central angle because the angle vertex vertex C is in the center of the circle. Therefore, it is called the central angle. Okay. Then we have the arcs. And if we have the arc from A to B, all right, we would call this guy the minor arc. All right, AB. And it's called the minor arc because basically it's less than 180 degrees. Less than 180 degrees. Then we have the other arc on the other side, and that guy is called the major arc. And we would call this A, D, B. And that's the major arc. And it's the major arc because it is greater than 180 degrees. So we call that the major arc. Now, if we had another line that went straight down like so, let's call it X and Y, right? That guy would be the semicircle. I reckon it would be the arc XY. We can actually it could be called two things. It could be XD Y going from the left, or it can be like XBY or XAY. There's a lot of ways to call it. But it's a semicircle because it's exactly 180 degrees. Right. So we have a minor arc, we have a greater arc, we have the semicircle. Those are the ways to describe arcs. If you have an arc that is less than 180 degrees, when you label them with two letters. So we had before in the previous circle a B. If it's greater than 180 degrees, then you could label it with three letters, and we had labeled it A, D, B. So usually bigger arcs tend to have three letters, while minor arcs tend to have two letters. Yeah. And there you go. Measure of a minor arc is measured as its central angle expression. Measure of AB is read as the measure of arc AB. So yeah, measure of AB is read as the measure of arc AB. The same thing. The major arc is the same thing. In terms of how it's read. Okay. Here we have the arc addition postulate. A, B, and here's our C way over here. Here it is from A to B, B to C, and basically the whole entire arc here, A, B, C, the major arc, we can say that the measure of the major arc, A, B, C, is the sum of the two smaller guys. The measure of AB plus the measure of BC. So just like angle addition postulate and segment addition postulate, arc addition postulate just says that the bigger arc is the sum of the two smaller arcs. You can add them and subtract them. Right, so that's arc addition postulates, and it is a postulate, not a theorem. Arc addition postulate. Also to note with central angles, it's implied here, but it's not necessarily said. So let's see. Let's say this is 50 degrees inside here. If angle ACB equals 50, and this is only with central angles only. If the angle is 50 degrees, then the arc length is also 50 degrees. They are measured both in degrees. Alright, so we have this circle. This is 120. This is 80. This is 60. That's T. That's Q. S and R. Alright, they want to know what TQ is. Well, from the arc length T to Q. So TQ, since the central angle is 120, it's the same measure as the as the arc. So TQ is 120 degrees. QRT, QR, and then T way over here. Well, in order to find what RS is, they all measure to 360 degrees, right? So we have 120, we have 80, so that's 200, we have 260, and then full circle is 360 degrees on one rotation, so we have 100 left. So this is 100 degrees. So QRT, so from Q to R is 60, R to S is 100, that's 160, and then S to T, that's 240. 240 degrees. Then we have TQR. TQR, so that's 120, and 60, so that's 180. And then QS. QS is 160. 60 plus 100. TS TS is 80. And while it is 180 TQR, we can also call it a semicircle. So I'll just put semi right there for a semicircle. And then RST. RST, which is also a semicircle because it's 180. Okay. So, are they major or minor arcs? This guy is a minor, has 2 letters. This guy is a major, has 3 letters, but it's also greater than 180. Alright, this is just a semicircle. This is a minor. Less than 180 has 2 letters. This is a minor. And then that's also a semi. So if you have 2 letters, what your description is, that's your indication that it's a minor arc. If it has 3 letters, then it's a major. Or if it's greater than 180, it's major, or less than 180, it's a minor. All right. All right. Congruent circles have the same radius. Congruent arcs they have the same measure of the arc. So let's go through a couple of these and what they look like. So if we look like up here, we have this circle. It's the same circle, so I know that they're going to be congruent. The radius are congruent, right, from the center out. So if this is 80 and this is 80, then the arcs are also 80. So I know that these are two congruent arcs and two congruent angles and two congruent radii. So they're all congruent. The arcs are congruent. Here we have a little circle and a big circle. They are not congruent because they don't have the same radius. From the center to R, it's not the same distance from the center to T. So these are not congruent circles. Since they're not congruent circles and they don't have the same radius, then these two arcs are not the same. RS and TU, even though they both have the same central angle, these arcs are not the same measure. They're just because the circles are not congruent. It only works when the circles are congruent. In this case, the circles are not congruent. All right, here, I'm told that the radiuses are the same from here to here. Therefore, they are congruent circles. So then VX and XY as arcs are also congruent because congruent arcs happen within congruent circles. So the arc is 95 and the arc here is 95. So congruent arcs, not congruent arcs, congruent arcs. All right, so 7 is same as that one example. We have a circle, have the same radius. So then I know that these two circles are congruent and they have the same central angle. So then if they have the same central angle, then they have the same arc length. So CD arc length is the same as arc length of AB. So they are congruent arcs. Here, even though they're the same central angle, the radiuses are different. Radii, radiuses. PQ, or Q to the center, and M to the center. This is 5, this is 4, so these are not congruent circles. If they're not congruent circles, then these arcs are not congruent as well. So no, they are not congruent arcs. So that's section 10.2. Then we have chords and applying them chords. So remember that a chord is some segment that connects two parts of the circle, right? The endpoints are two parts of the circle. And then we have the diameter, which is also a chord, but it's a chord that goes through the center of the circle. All right, so this is the diameter. This is the chord, a chord. When you have a diameter, right, it breaks up the circle into two semicircles. So we don't have any major or minor arcs. We have semi over here, and we have semi over here. Right? The diameter is the biggest chord in a circle, and when it goes through, it creates two semicircles, or where the arcs are the same. However, if we have a regular old dandy chord, a chord would break a circle up into major and minor arcs. We would have a major arc over here, greater than 180 degrees. And we have a minor arc down here, less than 180 degrees. Right. So that leads us to theorem 10.3. And what theorem 10.3 says is that if we have the same circle or two congruent circles, and the chords are the same, then their arcs are the same. So we have A, B, oops, I'm tripping. We have A and B. We have C and D. So, and we have their minor arcs. So this guy and this guy. All right. So this is what 10.3 says. If A, P, the arc, is congruent to CD, their arc, then I can say oh, it's an if and only if. If and only if their chords are the same. So chord AB has to be congruent to chord CD. Okay. If the minor arcs are congruent, then the chords are congruent. In a congruent circles or the same circle. So this is one case scenario, or the other case scenario is we have two congruent circles. Just pretend that they're congruent. And these two chords are the same. Alright, so this is A, B, this is C, D. So if they're the same, then these arcs would be the same. Alright, so it works in one circle or two congruent circles. But for these theorems, they're going to all put them in one circle. So just keep that in mind, but it still works with both. Alright, so that's 10.3. Here. They say that AB is 110 and find BC. Well, since they're congruent chords, then we can say that their arcs are congruent, their minor arcs. So then AB is going to be the measure of AB, arc AB, BC. Measure of arc BC is going to be also 10 degrees. And if AC was 150, then what is AB? So here's how this one works. So they share the same point here at B. I know that these two guys are the same, right? Which means that these two guys are also the same. Right? These arcs are also the same. Alright, so if I know that the whole thing is 150, I could just say that this is x and this is x. And I can say 2x equals 150 because I know that they're the same, and then divide by 2. X equals 75 degrees. So the measure of arc AB would be 75 degrees. Bisecting arcs. This thing says that if we have a circle and we have a central angle x, which goes out to x and y, we have some line that goes through C. This is Z. We have some line that goes through the center at, reaches out to y. So they're saying that if xy is congruent to yz, then any point that goes through y, ray, line, segment that goes through y, it must be the bisecting, the arc bisector. So this is saying that if it's a bisector, then it cuts it in half. So xyz is cut in half at y, and anything that goes through y must be the bisector, which makes sense. Alright, theorem 10.4. 10.4 Says that if a chord is a perpendicular bisector of another chord, then the chord is diameter. In a circle, we have a chord. Tiara. We have a circle. I mean, a chord that goes through the center. So this is the diameter, and it intersects at point P. This is diameter SQ. What this theorem says is that if this chord SQ is the perpendicular bisector of TR, then this chord must be the diameter. So if QS is the perpendicular bisector of TR, then SQ or QS is the diameter. Okay. It has to be the perpendicular bisector. The only thing that's the perpendicular bisector in a circle is the diameter, essentially. Theorem 10.5 says basically the converse. The diameter circle is the perpendicular bisector of the chord or is perpendicular to a chord, then the diameter bisects the chord and its arc. All right. So if you do the same thing. If QS is the diameter, and perpendicular to TR, then it bisects TR and arc TR. So that means that TP equals PR and TQ congruent is congruent to RQ. Alright, so not only is the chord bisected, but also the arc is bisected. In this case, we have a diameter BD, center A. We have CE up here. I know that it's perpendicular. This is 9x. This is 80 minus x. So they want to know what the arcs are. Okay, so CD. First thing to do is set them equal to each other because they are congruent. So 9x equals 80 minus x. the other side, so 10x equals 80, x equals 8. Now that x equals 8, I can plug this in. So that's 8 times 9, and that's 72. Could plug 8 over here. 80 minus x is also 72, which makes sense. And then if I add those together, then that would be 144. So CD is 72 degrees. The measure of CD, the measure of arc DE is also 72 degrees because it's bisected, and then the measure of CE is 142 because you add them up. Theorem 10.6. Alright, we have chord here, and we have some chord here. Call that AB. Call that CD. We have the center, and this guy is perpendicular to the center, and this guy is perpendicular to the center at point G and at point F. Okay. Alright, so what theorem 10.6 says is that if I have some center of circle and the chord goes out from the center to the chord here and center to the chord here, and their distances are the same, then the chords are the same. So AB is congruent to CD if and only if EF, the E right here, is congruent to EG. Alright, so this guy and this guy, if it's congruent, right, they have to be perpendicular to the chords and congruent, then I can say that this guy and this guy are congruent. Okay. Note, since this is perpendicular, if I was to draw this line all the way through, that would be, the diameter. So then that means that this chord would be cut in half. And then likewise over here, it would go through here and be the diameter and cut that chord in half as well. It's implied. And the same chord or congruent, the two chords are congruent if and only if they are equidistant from the center.